Okay, continuing with our interest rates and interest accounts, I want to define a function a of t. And we're going to define this function as the accumulated value sometimes called the future value, at any time t of an investment of $1. So if at any time t, so we're starting at time zero, an investment of $1 from time t equals zero. So from 0 to t. Which means if we invest more than $1, we simply have to multiply this by however much we're investing. The amount of money we have at time zero, say capital A of 0, then the amount of money we have at time t will be A of 0 times little a of t. Now that means we already know what this is for compound interest. Compound interest we have one plus I to the t. We can use rates with any time period. So that I is interest per whatever. And then t can be measured in whole units or fractional units. If I'm dealing with months, but my interest rate is in years, then I could use a fractional number of years to represent something either 7.5 years, 6 years and 3 months. I can work that fraction out. Days. We'll often see daily rates. So like we did on Tuesday, we use divide by 365. We will find sometimes that some calculations assume a 360-day year. 12 months of exactly 30 days, just to make the calculations easier. So there'll be a couple cases where instead of using 365, we use 360. We'll point those out as we get to them. Please notice what that really gives me is this equation. Instead of using A0, I'm going to use P for principal, A for accumulated amount, which means if you know any of the three of those, A, P, I, or T, you can solve for the other fourth. So sometimes we solve for time. What's the value of T here in terms of the other variables? How do I get T below? I got to divide out the P, so I'm perfectly good with that. Well, let me write out the intermediate steps. So we have A over P is 1 plus I to the T. What do I do to get T all alone there?
You also do the T squared, the T root of 1 plus I.
If I did the T's root, that would cancel the T's. I
Oh,
wouldn't have any T's left. How do we get something out of an exponent? I need a logarithm. So I really need the log base T. I'm sorry, not log base T, log base 1 plus I. This is the base, but that's horrible. So we do ln A over P over ln 1 plus I. In the same way, I can solve for the interest rate. There I'd use the 1 over teeth root, right? If I wanted to get I, I'd do A over P would be 1 plus I to the T. Then I could do the teeth root. And subtract 1 to get I all alone. If I know the accumulated value, I can work backwards to get the present value. If I know the present value, I can work to get the accumulated value. So I can work this in any way as long as I know 3 of the 4. But that's the same thing we did where we did, cross multiplying to find the unknown. We knew 3 of the 4, so we just cross multiplied to get the 4th. We're just not cross multiplying here. The algebra is a little more complicated. Questions? And aside, what if I wanted to know how long it takes to exactly double my money? I'm solving for time, so I'm going to use this idea right here. But if I'm doubling my money, what's A over P? If I'm doubling my money exactly, then I want to end up with exactly twice what I started, which makes A over P 2. Which means when I solve for T, I have ln of 2 over ln 1 plus I. Okay, people. A long, long time ago in Calc 2, we did Taylor series. And I remember there was a Taylor series for the log of 1 plus x. And it turns out that the log of 1 plus x's first Taylor is just x. So this is roughly equal to the ln of 2 over I. What's ln of 2? Y'all have calculators. What's ln of 2? Perfect. Which is roughly 0.7, well, give or take a little. All right, wait a second. If this is about 0.7 over an interest rate is a decimal, right? That's a percentage. Let's move the decimal place over twice. 70 over I as a percentage. So if I know the interest rate is 5%, it should take me roughly 14 years to double my money. 70 divided by 5 is 14. That's a really fast calculation. And this is referred to, hope surprising no one, as the rule of 70. And it's taught in a lot of quick finance classes. It's a fast way to figure out time series. How long is it going to take me to do something? Well, let's use the rule of 70 to approximate it. If we know the growth rate as a percentage. Questions? If you remember ln of 3, which I'm sure we all do, right? ln of 3 is about 1.1. Do the same thing to triple my money. 110 divided by the percentage. I have to know the log tables. I love short, sneaky things like this. Where did this rule come from? Here we go. Compound interest isn't the only accumulation function we will use. So our A of t accumulation function for compound interest is given, but there are other accumulation functions. Compound interest charges you or rewards you by depositing the interest and allowing it to continue to accrue. Simple interest just counts interest once. So in this case, our accumulation function is just going to add the interest to our initial deposit of 1. This lines up with the idea we started with on Tuesday, where I said that interest was principal times interest rate times time. Well, that would make my accumulated value principal plus principal times rate times time. Factor out the P. Oh, there's my accumulation function. A lot of financial instruments like promissory notes tend to use simple interest. A promissory note is basically a glorified version of an IOU. I'll sign the note saying I will pay you back this much on this date at this rate. Interestingly enough, they call their version of interest the yield rate. This makes me a little crazy because the word yield is going to have several different meanings depending on which situation we're in. And that means we have to be careful whether we're talking about yield rate for a promissory note, which then is simple interest, or the gross yield rate for other financial instruments, which goes back to our effective annual rate. There's an example in the text, example 1.4, between pages 14 and 15, that goes through a promissory note being exchanged between two people. But when you have a promissory note, you have an IOU, right? So here is a slip of paper, and it says, let's see, this slip of paper is worth $160. But it's not worth $160 until September 30th. So if you take this piece of paper and hold on to it for a month, they'll give you $160. Is this worth $160 to you today? Why not? I can't do anything with it today. It's like a gift card. I can only spend at one store that's not in my area. Thanks. What do I do with this piece of paper? So if it's not worth $160 to me today, I could say, well, wait a minute. Instead of me saying it's $160, I'll sell it to you for $150. Then you'll make $10 in profit between now and the end of the month. Well, then we could work out what your yield rate is on that. And sometimes this piece of paper happens to be one I'm making up right now, but things like treasury notes and government bonds are thought of in this same fashion and can be exchanged, bought, and sold in exactly this way. So if I have a promissory note, maybe it's good for 6 months. but I need cash today rather than tying it up and waiting 6 months. I'll sell it to you. And you're like, okay, now I have this and I have to wait 6 months, but I only paid 140 for it. All right, a month and a half goes by and suddenly you need money. What do you do with this? You can sell it. We can go back and forth and sell it. This becomes a tradable commodity. This piece of paper that is magically worth some money. In the example, there's a sell date of March 1st. One person sells it to another, and then they sell it again on March 1st. Look carefully at where they count March 1st versus where they don't. They go through by number of days. So we need to watch. I want you to read this example and watch where they count March 1st. Now, this is what's referred to as a fixed income investment. The note tells you how much it's worth. This piece of paper is worth $160 eventually. So what you're paying is a smaller price. If the yield goes up, if my interest rate goes up, then my investment price should go down. Because I have to invest less, I'll earn more interest. So price and yield are inversely related to each other. Lower prices on fixed income investments are correlated to higher yields. So, for example, right now, if we were to say interest rates go up, then prices on these income investments should go down. Same thing goes the other way around. Every time interest rates drop, my fixed income investments get more expensive. There's a really nice, easy to think of graphical difference between simple and compound interest. And that's that simple interest is a straight line. Compound interest is an exponential equation. But exponential equations get a lot faster, a lot quicker, the further out in time we go. But if you take the graph of an exponential equation and look at the beginning of it, right up here, close to where t equals 0, especially for small values of I, 10% and lower, this graph really does look like a straight line. So here's my question to you. Is that graph the graph of a straight line or an exponential equation? It's hard to tell, isn't it? It turns out that's the graph of 1.1 to the x. That's compound interest. But when I look at the beginning of this, that looks like a straight line, damn it. What we will see often is in time frames of less than a year, more banks will use simple interest than compounding. In longer term things, we'll use compound more often than simple. Compound earns more or charges more longer time frames than simple does. But in the short run, simple is literally just simpler. Some lending institutions combine the two and offer compound interest for years, and then for any fraction of a year, they convert to simple interest. So if you're going to do something for 7.5 years, you get 7 years at compound and then a half at simple. I have never run into one of these financial instruments in real life, but there's a textbook example at the bottom of page 16 that does exactly that. But my reaction is calculations are so simple and the computers are powerful enough, there's not really a reason to switch for the fraction of a year anymore. And a lot of places this practice has fallen aside, but it will show up occasionally. Let's consider, I think the example is 9% at 4 years and 5 months. 9% APR, 4 years and 5 months. If I do this as a single compound interest problem, I would say, oh, well, then my accumulation function as compound interest would be 1.09 to the 4 plus 5/12, or 1.09 to the 48 and 5 is 53 over 12. That's a really easy calculation, isn't it? I got a calculator in front of me. I'm done. 1.09 raised to the 53 divided by 12. So however much you're investing, multiply by this and you're done. If I do this split version, well, then what would I do instead? I would do, A of t is 1.09 to the fourth for the 4 years. And then I would multiply by 1 plus 0.09 times the fraction of a year. And that is the combined compound for the number of years, simple for the number of months less than a year. So when I type this in exactly like that, 1.09 to the fourth, went off the edge there, 1.09 to the fourth, then multiply by 1 plus 0.09 times 5/12, I earn a little bit more. Difference is in the third decimal place, right? It's not a huge difference. From looking at hundreds of dollars, we're talking about pennies. Questions?
You're saying that banks will do the second one?
I'm saying they used to more often than they do today. Now, more often, they just do the first one. But what's more advantageous to the person doing the lending? If they know that both options are available, they'll do both and say, oh, which way am I going to earn more money? Let's do that one. Because remember, the goal is for me to make money. It's to queue over as hard as I can. From one perspective. However, that's why the Truth in Lending Act exists, because the Truth in Lending Act requires me to take what would really be happening here and convert it to a calculation like this and give you this rate Instead of 9%, it would be like 9.018%. If I go back and work out what the actual APR is using this method. And that's why we got away from using this, because of the truth in lending ethic. It requires me to give you an effective annual rate. So you might as well use that rate for what we're going to do. So we have an accumulated amount function, right? Capital A of t is A of 0 times little a of t. And that means we can think of this as a function I can do net change in. Wait a minute. If I have 2 times, I can ask how much did my accumulated value change? Huh. If I know any 2 times, I can then work out a rate per that time. Frequently, we do this as 1-year periods. So let's see. A of u plus 1, I'm sorry, t, not u, t. A of t2 is A of t1 plus 1. So that would be A of t 1 times 1 plus whatever the interest rate is at time 1. I did it again. I t1. Right? 1 plus I times the time, but the time here is 1. I'm only adding 1 year. Oh, well, that allows me to say that the interest rate, I'm sorry, this should be T2. The interest rate at time 2, resolve this, I get AT2 minus AT1 over AT1. Or AT2 minus over AT1 minus 1. Hey, wait a minute. Change in value minus 1, you get 1 plus I. That's my interest rate. That makes sense. So if I have things like the stock market, Dow Jones Industrial Average, I can get rates for different days and times. I can get values at different points. Figure. Here's my return on the Dow Jones information from 2017 to 2022. If it was 1 at the end of 2017, then I can go back and forth and look at all these different values at different points in time. I can say, oh, what was the interest rate between 2017 and 2018? Or between 18 and 19, or between 19 and 20. I can do this linear interpretation, and I can get an interest rate for all of these. But that means this, in 1-year periods, looks like a step function. Wait a minute, I've heard that term before. Right, step functions look like like stairways, so I can actually get level changes of interest rate. That's a discrete version of the continuous function we want A of t to be. Our exponential function then gets replaced by a set of steps. and then charge in discrete amounts of time. Questions? I said it when I was talking about the promissory note. This piece of paper is worth $160 in a month. So let's reverse the calculation. I want to end up with 1 month from now, some value of money, A. Well, then I can reverse this and I can say, oh, the amount I need today is A divided by 1 plus I. We'll sometimes write that as A times 1 over 1 plus I. This is my present value factor. Sometimes it's called a discount factor. We're going to also define this by the letter V. So you're going to see the symbol V a lot. V is just 1 over 1 plus I. I did tell you that there are a set of formula sheets from the actuarial economies for the exams. I want you to use these. They're on our Canvas page as a handout. I want you to notice there's our definition for V right there. 1 over 1 plus I. We're going to see V in a lot of these calculations. I'm going to use that. I don't write V very often. I tend to write 1 over 1 plus I. But when you jump to the book, formulas in the book, you'll see V a lot. I just didn't grow up with that piece when I learned this material. If there's more than one possible interest rate involved, then there could be more than one possible discount factor involved, in which case we'll call it VI so that we know what rate it goes with. So something like V 0.05 is 1 over 1 plus 0.05. That way I've got the number there for I. This is really just taking that accumulation function and working it the other way. So if I had, let me write that formula again, A equals P1 plus I to the T. Oh, wait a minute, that's now wait a minute. No, we were looking for P. So how do I get P? P is A over 1 plus I to the T. So that's A V to the T. Those look almost exactly the same, don't they? It's which side what's on, and that's the reciprocal behavior between 1 plus I and V nailed out. So let me see if I can put this into practice. You win a prize in a lottery. It's going to pay you $5,000 a year at the end of the year for the next 4 years. Today is August 28th. On August 27th of 2026, you will receive a check for $5,000. Same thing in 2028, 27, 28, and 29. So you get $5,000 a year from now for 4 years running. I need to put enough money away to be able to pay you that. I need to go to the bank, stick the money in an account, and know that I will have enough to write you all these checks. How much do I need to put in the bank right now? What's the present value of this sequence of payments? Let's assume that I can get a nice, easy interest rate. I'm going to get 6%. How much do I have to put in the bank right now? Well, let's do some visualizing. Here's today. Here's a year from now, 2 years from now, 3 years from now, 4 years from now. This will be time. I need to write you a check, $5,000. 4 times. How much do I need on hand today to write you that check in a year? I want to take this $5,000 and back it up to today.
Would be 500 divided by 1.06.
Or 5,000 V 0.06, right? Yes. So do that calculation and you'll come up with some number. What is it?
$4,716.98.
But now I have to do this 3 more times, right? To do this payment, back to today, I've got to come back 2 years. So this time, it's 5,000 V 0.06 squared, or 5,000 over 1.06 squared. So I got to divide by another 1 point, because I'll earn interest if I leave the money in the bank. I'll earn interest at the end of year one on this much, and that'll bring it to $5,000. But here I'll earn interest not just at the end of year one, I'll also earn interest at the end of year two. So I'll earn more interest. I can leave it there longer. What's this number?
It's like 1,449. 498.
And then I'll do it again for this one. But here, what will I use?
EQ.
And here I'll use v to the fourth. So my total present value is hey, wait a minute, that's a sum, right? And they all look pretty much the same. For your benefit on the calculator, there is, under the math option, a summation function down there at number 10. So if I can write this as some sigma, that'll make my life easier. And I can think of this as starting at 1 and going to 4. So if I say we're going to let A go from 1 to 4, then I can do 5,000 divided by 1.06 raised to the A. And it'll add it all up in one fell swoop and give me a total $17,325.53. I am a lazy person. I want to do as few calculations as I can, as many times as I get away with it. So I'm going to shrink the actual amount of calculating I have to do down wherever possible. This is a good example of that. Rather than do 4 separate individuals, let's do it as one giant thing. But notice that requires me to write it all out and understand that that turns into something I can use. Questions? Talk to me. Here are a couple more present value calculations on page 20. Problem actually starts here. Ted wants to invest in a bond. It's called a zero coupon bond or a stripped bond. In other words, he puts the money in, it disappears, he sees nothing, hide nor hair of it for 25 years. In 25 years, the fund has had an average annual compound rate of 19.5%, but sometimes it's been as low as 2 and as high as 38. Assuming the average growth rate, he wants $1 million, right? Wants to end up with $1 million. What does he have to put in the bank right now? Well, there's my present value calculation. At the average rate, the present times in, this is A of t, should be equal to $1 million. There's my V right there, reversing that process. On the other hand, it's possible that we could go to a guaranteed investment at 11.5% instead of using the fund at 19 average. That's guaranteed. It says so right there. So that's why it's a lower rate. We're guaranteeing it, but you could earn as much as an average of 20%, maybe as low as 2, maybe as high as 38. Which one do you want? The sure investment of 11.5 or the average of 19? Well, that's going to change the amount you have to put in the bank substantially. If you assume a 19.5% growth rate year over year, you only have to put in $12,000 to be worth $1 million 25 years from now. If you assume an 11.5% rate, you need to put in 66. That's a hell of a difference right now. If I say, well, I only have 25,000, I could definitely do this, but what rate would get me the right thing? Well, then I can take this and solve for the rate. If I really want to get to 1 million and I take this amount, but I put it in the 11.5% thing, how long is it going to take me? Well, it's not going to take me 25 years. It's going to take me almost 41 years. Questions? Treasury bills work this way. There's an entire discussion here in this section on using simple interest instead of compound interest to do present value on treasury bills. Here's an interesting note. If you go to the Treasury website, treasury.gov, it's on the list of web links on our Canvas page. You can find the American equivalent of this. And it shows you when they put the bills up for sale, when the deadline is, how long they're going to last. So this bill is issued October 13th. It comes due 98 days later on January 19th. This is just an identification number. This is the total amount of bill that we are offering. So notice that says in $M. What's M? Well, in this case, it's millions, which means this is $9,200 million of, do you want to buy some of this? They've got 9.2 billion available for you to invest in. Average price, what the hell? That column is the price you pay today for $100 worth. So if you want to buy $100 worth of stuff 98 days from now, I'll give you $100. You have to give me 98.98319 today, which gives you a yield rate of 3.826%. This rate is calculated using simple interest, as opposed to compound, because we're under a year, right? Under a year, simple interest is preferable. You should, this is just the first one. But you can repeat this. Notice they're using 365 days for their year. 98 out of 365. We should check the other two. So we have a 3-month, a 6-month, and a 1-year, effectively, bill. The US bill market works the same way. Questions? There we are. So I have a future value, I have a present value. And I think of all of my transactions either starting today and ending there, or I know how much I want then, let me work it back. I can really do it from either end. As a matter of fact, I don't have to pick an end to write out my idea. If I want to write a sequence of algebraic expressions for financial transactions, interest rates, amounts that go out, amounts that come in, disbursements and receipts, all have to be included. The dates, therefore, include time periods. But those can be time periods previous to today or forward from today. I can say, oh, everything is going forward from today, or everything is going back from today, or I could put my day somewhere in the middle. That's called a reference time point. or sometimes it's called a valuation date. And once we have this idea, I need to find the value on that day of all the money that needs to go out and all the money that needs to come in. Whether the time it goes out is before today or after today, whether the time it comes in is before today or after today. So I need to balance out two things. I need to know how much in the past payments I made out accumulated and how much moving forward, I'm sorry, moving back to today, how much all the stuff I will have to pay is worth. And then I need to balance that with the ins. The accumulated value of all of the money I've already gotten plus the present value of the money I'm yet to receive. Once I do this, I set the ins equal to the outs. I create what's called an equation of value. I want to work through the example in the text for the unluckiest gambler alive. Every Friday in February, Friday the 7th, 14th, 21st, and 28th, Walt bets $1,000 at the track. They give him credit at a weekly rate of 8%. So we're doing all of this in weeks. Unfortunately for Walt, he's not a good gambler. He loses all the bets. So he goes to his bookmaker and says, I agree, I will pay you. all of the money back on March 7th, 14th, and 21st, Walt pays $1,100 each week. Is Walt done paying his IOU off? Does Walt still owe money at the end of March 21st? He borrowed $4,000, right? He paid 4 bets worth 1,000 each. He's only paid back 3,300. So at the end of March, on March 28th, he's going to pay some amount of money to be square. I want to know how much he's going to have to pay. Okay. I'm just going to draw a timeline like we did with the $5,000 payment. I'm just going to draw a timeline. So let's figure this out. On February 7th, 14th, 21st, and 28th, he borrows $1,000. So there's $1,000 here. And all of those are money that we have to decide whether it's positive or negative. Are we thinking of this as money we loaned out? Or are we thinking this as Walt as money we brought in? It's up to you. But these are outs. So I'm just going to write out. This is money out for now. Out to Walt. So I'm picturing myself as the bookie. I loaned the money. Now I'm going to bring in the money. On the 7th, we have $1,100 in March, $1,100, $1,100, and then X. And these are in. By the way, if you reverse the word in and out, the problem stays exactly the same. We just have to know which direction the money is moving for each payment so that we know where on our equation it goes. Now, in order for me to figure out X, I need my equation of value, which means I need a valuation date. We can pick any date we want. In the textbook, here on page 23, they do two different calculations. They do one with this valuation date. And they bring all this money to present value. They do another one with this as the valuation date. And they bring all the money to future value. We could do whatever, we could pick this date. It doesn't matter. We have to decide where we're going to put the valuation date. I deliberately picked a date that wasn't either end because either end is in the textbook. So I'm going to use the 28th of February, just so we have a different example from the textbook. So I'm going to put a star right here. That's my valuation date. This is my choice. I pulled this out of my ass. So let's think about the amount of time it takes to bring these things here and to bring these things here. Right? Then everything will get balanced right around this. So this payment is going forward in time. This $1,000 goes forward 3 weeks, right? 7th to the 14th, to the 21st, to the 28th. And we're earning interest, being charged interest, at 8% per week. So the future value of this is 1,001.08 cubed. That's this one. What about the $1,000 that was borrowed on the 14th? And the $1,000 on the 21st? And this $1,000 that is borrowed on the 28th itself, how much interest does it get charged? None. Those are the outs. The outs have to equal the ins. So now I can say the outs have to equal the ins. So let's do the ins. March 7th, that payment of $1,100. What's the factor I need to multiply that by? That's our V value. Yeah, we're doing a present value. That's V, 1 over 1.08. So I could also write that as 1,100, 1.08 to the negative 1, right? Moving back in time, the t value is negative. Divide by 1.08 or use V 0.08. Those are all equal to each other, right? So I use whichever notation you'd like there. What about the March 14th payment? Pi day.
Divided by 1.08 squared.
Exactly. And then the payment on March 21st and on the 28th. Now notice, there's the x that I want to solve for. Ready for the sneaky part? I'm going to multiply by 1.08 to the fourth. Why am I going to do that? If I multiply by 1.08 to the fourth, what's next to this x? 1. So this becomes 1000, 1.08 to the seventh, 1000, 1.08 to the sixth, 1000, 1.08 to the fifth, 1000, 1.08 to the fourth equals 1100, 1.08 to the third, plus 1100, 1.08 to the second, plus 1100, 1.08 to the first, plus x. Now you can solve for x, can't you? Go ahead.
Could we take, like, could we factor out the just for regular?
1000, 1.08 to the seventh, plus 1.08 to the sixth, 1.08 to the fifth, 1.08 to the fourth. Oops, parenthesis goes there. Equals, I'll do it on this side too, 1100, 1.08 to the third, plus 1.08 to the second, plus 1.08, plus x. Now all I have to do is figure out what those two numbers are and subtract. Now it turns out that the equation that is currently at the top of the screen is the same equation you would get if you used the valuation date of March 28th. So let's do the actual arithmetic. There's the left-hand side, the thousands, the outs. I get 6,130. I'm going to use all the decimals at the moment. 6130, 51562. Although I'm pretty sure that my bookie would just say 52 cents. Now I'm going to do the right-hand side. 1100 times 1.08 to the third plus 1.08 squared plus 1.08, 3856, 7232 plus x. So literally all I have to do is subtract. I take this number minus the one I just came up with, and I know that I owe a lot more than 1,100 bucks on that last week. Questions?
So for this, we can pick any point as well.
As a matter of fact, here in the textbook on page 23, they did this first payment with a valuation date here at February 7th, right? So notice That means they have to bring everything back. So there are no 1 plus i's, they're all v's. I don't have to bring this at all, so that's just 1,000. I brought this back 1 week, so that's 1,000 times v. I brought this back 2 weeks, 1,000 v squared, 1,000 v cubed, 1,100 v to the fourth, 1,100 v to the fifth, 1,100 v to the sixth, x v to the seventh.
And so with this, since we have to do like negative powers to begin with and then change everything, but it's the ends, we don't have to.
Well, but notice that those really are negative powers, right? Because that's 1 over 1.08. So that's 1.08 to the -1, -2, -3, -4, -5, -6, -7.
Yeah.
If I choose this as the valuation date, then all of my powers are positive.
Okay.
You can pick any valuation date you want. As long as you move the powers appropriately to that valuation date, you'll get the right answer. And that's why we now have 3 different valuation date calculations that all give me the exact same dollar figure.
Whenever you do these, you think we should just always draw them out?
I like drawing them out because I think that helps a lot, but I'm a very visual person. It actually has taken me quite a while to figure out how to do those drawings on the computer properly, but by hand, that's really easy, and I think that's very helpful. Again, that was how I was taught, and that's, oh, good Lord, back in the 90s. So, been a long time. I'm used to doing time diagrams like that. I know a lot of actual finance people actually do this by calendar. So they pull out a printout of a calendar and draw things back and forth on those. I get it, but it's a lot blockier and a lot harder to follow to me. I try and do it on one line wherever possible. It ain't always easy. More questions? Joe, if you want to ensure that you're using positive exponents, you should use the furthest forward date. Then everything has to get brought forward in time, and all your exponents are going to be positive. If you don't really care one way or the other, then pick whichever one you think is most convenient. A lot of people will say that they prefer that end date. That's the day I know everything is done here. A lot of people prefer today, whatever today is, whether that means I have some payments in the future and some payments in the past, or everything is going forward from today. But it's going to depend on the situation in our problem. Make sense?
So then you were going to, the end date, you brought everything to X. Or X were already by itself. Because X.
Yes. Yes. Well, actually, no, because our balancing would be X is an in, right?
Yeah.
These are still ins. So it's still outs and ins. What would change are the powers.
Oh, okay.
Right, now think of this. We're bringing stuff forward, right? We don't have to bring X forward at all. That's exactly this equation, isn't it?
Yeah.
This is the equation we get right here.
So you wouldn't have to have done the times.
Minus whatever, right?
Yeah, okay.
I didn't have to move the X. It doesn't have any 1.08s with it. Everything else had to move up to that date. So all I end up reshuffling by picking a different date is where the exponents are. Okay. Officially, we ran through section 1.3. The homework questions are divided by section. You should start. I know they're not due for a while still, but please start looking at these and bug me about them. Ask me questions. I will tell you, this is a matter of familiarization. The math looks disgusting, but more often than not, the word pisses me off are the words. Translating English into geek speak is the hardest part of this. We will do more on Tuesday. I will see you then. I'm going over to the enrichment center shortly. Have a wonderful rest of your day, people.
So the sign says ten place.
Outs versus ins, yeah. Yeah, that's the best part about this. Money coming out has to equal money coming in. Let's figure it out from there.